Our goal today is to see whether or not Jason is getting the maximum distance possible with his shot put throw. So we have a problem here where he throws the shot put from a height of 2.3 meters. We're going to assume without growing any taller, that number is not going to change. We put that as our delta y because the shot put starts at a height of 2.3 and lands on the ground. We're going to use negative 9.8 and we're going to assume Jason's not going to change planets. This throw went 52 feet, which is about 15.85 meters. Using video analysis, we found how long it was in the air, and it was in the air for about 1.8 seconds. So based on this information, we should be able to find the horizontal velocity, the initial vertical velocity, and the final vertical velocity. So go ahead and do that. When we work through our equations, we find a horizontal speed of 8.81. We find a vertical speed of 7.54 at the moment of release. And we find a landing speed of about 10.1 meters per second. Once you have these numbers and you properly place them into the chart, you're then going to draw your launch triangle showing the speed of the ball horizontally, vertically, and then you'd like to find the hypotenuse and the angle of launch. So take a minute and do that. Okay, so after we put in our horizontal and our vertical velocities, we find that Jason threw the shot put at a speed of 11.59 meters per second at an angle of 40.55 degrees. What we'd like to do today is try to evaluate, is that the best possible angle that he could throw the shot put? We know that 45 is the best when we go from the ground to the ground. But what about when we start at a height? What is our best angle? Blank spreadsheet. You're going to start by listing your constants at the very top. So we're going to have delta y, and the delta y we're going to use for Jason will be negative 2.3 meters. We're then going to have our gravitational acceleration, and we're going to have that at negative 9.8 meters per second per second. And then finally, we're going to have our velocity, and we're going to assume that he throws it with a speed of 11.59 meters per second. It's probably a good idea to go back and put our units. Again, don't put them with the numbers, but put them with your descriptions. Okay, you are now done with the constant part of your spreadsheet. To do is try seeing how far the ball would go if Jason were to throw it at a bunch of different angles. So we're going to start with a column called angles. We're going to put it in degrees. We're going to start with 0, and then we're just going to increase it by 1 degree at a time. Don't type them all out, just do a couple of them. Highlight those ones that you typed in. Go to the bottom right corner where you see the little blue box and just pull down. Pull all the way down until you get down to about 89 degrees. We don't need to do 90 because we know that will go straight up and straight back down again. Okay, so that'll be about 93 rows, get you to 89 degrees. Computer doesn't work in degrees, it works in radians. So our next column, we're just going to type angle again, but this time we're going to do it in radians. We're going to have the computer do all these conversions. So we're going to type equals, then we're going to type in box A4, which would be our angle of 0 degrees. We take the degrees, we multiply it by pi, and then we divide it by 180. So notice again what we typed in, equals A4 times pi, parenthesis, parenthesis, divided by 180. We then hit enter, and it will do all of these calculations. It will suggest an autofill, and we're going to click yes. This will have converted all of our degrees into radians, all the way to the very bottom. Make sure 89 degrees is around 1.55 radians. For angles in radians, we're now going to figure out the velocity in the x and y directions. Because he's throwing it on an angle, we have to do our trig to get velocity x and velocity y. So to do that, we're going to type equals, and it will be equal to the hypotenuse of our triangle, which is found in box H1. Now it's very important to keep it as a constant. We're going to do $H, $1. That will make sure that it always uses the same box and doesn't move it left or right or move it down as we fill down this equation. So we take the hypotenuse and we multiply that by, for x, the cosine of our angle. Our angle is found in box B4. We then want to autofill all the way down. We should see at 0 degrees, the x velocity is equal to the total velocity because we're not on an angle. And then we should get smaller and smaller numbers all the way down. And at 89 degrees, we should get an x velocity of almost 0, 0.2. Okay, we do the same thing for y, but for y we're going to use sine. So we type in the location of our velocity, which is $H, $1. And this time we're going to multiply by the sine of angle B4. Okay, the sine of the angle which is found in B4. Okay, notice I put a multiplication sign in there. I was not supposed to. It is sine of B4. Allow it to autofill. We should get no y velocity when we have no angle. And by the very end, our y velocity should almost be equal to 11.59. We now have our velocities for x and y for every single angle. Do is calculate the final velocity of the projectile. That is the velocity as it's hitting the ground. To do this, we know that we want it to come out to be a negative number. And we get this by doing the square root of the initial velocity, which is box D4 squared, plus 2 times the acceleration, which would be $E, $1, times $B, $1. Again, E1 and B1 are constants, so we want to use the dollar signs to keep those numbers constant as it fills our formula down. The D4 is not a constant, and we do want that to change for each of the successive boxes. Okay, so once we got our formula typed in, we hit enter. It didn't automatically fill it down for us, so we're going to do that manually. We go over and we grab the little blue box, and we pull it down to our last angle, and we've now calculated our final speed for all the different angles. Step is to figure out the time it's in the air. And for this, we're going to use the formula. We're going to take our final velocity. We're going to minus our initial velocity. And then we're going to put those in parentheses, and we're going to divide by our acceleration. Again, our acceleration is a constant, so we want to use dollar signs. So it would be $E, $1. We're going to fill it down, and we've got the time in the air for all of our different projectile throws. Finally, we want to get our delta x. And for the delta x, we're just going to take that time that we just got, and we're going to multiply by our x velocity. We're going to fill that down, and we're going to get the distances traveled by the projectile at each of the different angles. At this point, we want to see which angle will give Jason his best throw. So when we look at these things, we can see that we maximize our distance somewhere around the 41-degree mark. Okay, somewhere between 40, 41, and 42. And that is right about the angle that Jason released the projectile. So, although 45 was expected to be our best angle, that is only true if we start and end at the same height. When we have a height like Jason did of 2.3 meters, our best angle is somewhere around 40 to 42 degrees. To graph this out. So we're going to highlight just from row 3 all the way down to our last angle, which for me is row 93. So I highlight the entire data section, including the heading. I am then going to go to Insert, Chart. I get a chart popping up, and then I'd like to modify this chart to be able to see the things that I need to analyze. I'm going to shrink this over so we can see stuff. My x-axis, I want to make sure I set this to an angle. I want to make sure my chart type, I'm going to set to scatter. I am going to turn off all of the y-axes except for the distance. That's all I even cared about. And then this chart shows me how far the shot put went for each of the different angles. And again, we could see it maximizes somewhere around 41 degrees. The beautiful part about all this is if we wanted to go in and change the height from which he threw it, or the acceleration due to gravity, or the speed, our chart and our table would change dynamically. So again, if we threw it from the ground, we see our thing changes totally, and we now maximize around 45 degrees like we saw in lab. If we had thrown it from an even higher height, maybe 10 meters, we throw it off of a balcony on a building, we can see that we get a maximum angle somewhere in the high 30s, definitely below 40. So we could see that the higher up we start our throw, the smaller the angle that will maximize our distance.